Okay, so let's go ahead and keep going on slope fields. And there's only a couple of things that you're really gonna be asked to do with a slope field. One is to construct the slope field given a differential equation. The other is to go ahead and, like, given a slope field, you may be asked to actually fit a curve to that slope field, and I showed you that just a little bit in this past one. Um, the other thing that you may be asked to do in the interim, I mean not on the AP exam or anything like that, is you may be asked to do a little bit of matching, because that definitely helps you to understand how to think through slope fields and actually what they are representing. So the first thing, however, let's go ahead and actually construct some slope fields. Now this right here is a worksheet that is common to just about every single calculus teacher out there, and it's it's online in 1,000 different variations, and it was actually written by a veteran calculus teacher just right around the corner from us, right around the corner from y'all, at Clemens High School. I actually never had the pleasure of meeting Nancy Stevenson, but she has a great reputation for having been a great calculus teacher. So we'll go ahead and walk through a couple of the pages of her worksheet, because basically, as far as I'm concerned, nobody's really done it better at this point. Now, when we're given something like this, we recognize the fact that dy dx is equal to x plus 1. Now this one is relatively straightforward and relatively easy, okay? And because of that, we can actually think ahead. Let me go ahead and see if I can zoom, and that'll make it a little bit better. Okay. It's easy to actually think about this one and think backwards to what the function was, right? It was 1/2 x squared plus x plus c, right? So you can actually just do the integration in your head. But let's actually think through it just a little bit more straightforward in terms of treating the differential equation as a differential equation, okay? So when x is equal to -1, I'm going to get a derivative of 0. So when x is equal to -1, I'm going to get 0. When x is equal to 0, I'm going to get a slope of 1. When x is equal to -2, I'm going to get a slope of -1. When x is equal to 1, I'm going to get a slope of 2. And when x is equal to -3, I'm going to get a slope of -2. Okay. And I could continue to go up here. I mean, this is going to be 3, slopes of 3, and slopes of 4. And that should be what the slope field for that particular differential equation looks like. Okay? Because and of course, like I said, I happen to know that if you were to separate it, right, you could anti-differentiate both sides, and you're going to get something like this as what's called the general solution to the differential equation. And of course, that's pretty much what that looks like right there. Remember that middle term is what shifts you off of the y-axis, either to the left or to the right. And if it's positive, it moves you to the left. And therefore, I know that I'm going to have vertices in this family of curves at x is equal to -1. Okay, well that was easy enough. That one, however, was simply dependent upon x. Let's work on one that's simply dependent upon y. Now, this one is going to be a little bit different. And I know that where y is equal to 0, the slope is equal to 0. So where y is equal to 0, the slope is equal to 0. Where y is equal to 1, the slope is equal to 2. Okay? Where y is equal to -1, the slope is equal to -2. Okay, and to estimate this, basically what I'm doing is I'm aiming this at that point right there, because I know if I connected those 2 points, I would actually get a slope of -2. Okay, and if I go up here to y is equal to 2, I know that I'm going to get a slope of +4. And of course at 3, I'm going to get a slope of +6. Down here at -2, I'm going to get a slope of -4. Okay? Well, this kind of looks like it goes along here and then really quickly does that number. What do you suppose that describes right there? Well, this actually is a separable differential equation, and you can do it like this. Well, what's going to happen here? You're going to get a natural log, and then in order to solve for y, you're going to have to exponentialize both sides in order to get rid of the natural log and leave y by itself. And it's that exponentializing to undo the natural log around the y that's going to give you this exponential function. Okay? Now, we did one that was wholly dependent upon x. Then we did one that was wholly dependent upon y. Let's go ahead and do one that is dependent upon both x and y. I think this is pretty instructive. Now, the first thing that I did, notice the first thing that I did on the first one is I did these numbers right here. I figured out when the derivative was going to be equal to 0, and I put in those numbers first. The same thing over here with number 2. The first thing that I did was I determined where the slope was going to be equal to 0, and I did those first. The question is, when is this going to be equal to 0? Well, let's go ahead and find out. When is dy dx going to be equal to 0? Isn't that when y is equal to -x? Okay. Well, if y is equal to -x is the point at which I'm going to have a slope of 0, then I have 0, 0, 0, 0, and 0. Okay. Now, if I actually move off, and I can actually do this again for 1 if I wanted to. Let's go over here in the margin, and let's say I want when is x plus y equal to 1? Well, isn't that when y is equal to 1 minus x, or -x plus 1? Okay, well, -x plus 1, if I look at that, is basically this right here, right? Right along there. And so I know that I'm going to get a slope of 1 at those points. Okay. I could do it again if I wanted to for -1 is equal to x plus y, and that would be y is equal to -x minus 1. And so I would basically get these. Okay, well, basically what's going to happen is I could just go ahead and solve this and say, well, y is equal to -x plus y prime. And that could actually be a little bit easier in terms of helping me out. Now, I know that y is equal to -x plus 2 is going to give me slopes of 2. So 2, slope of 2, slope of 2, slope of 2. -x plus 3 is going to give me a slope of 3, 3, 3, steeper at 4 and 5. Okay, over here at -x minus 2 is going to give me a slope of -2, and then -3, and then -4, and then -5. Okay. Let's go ahead and look at that on a little bigger frame. Okay, and I think I've done this one before, but let's go ahead and look at it again. X plus y, and let's graph it. And that, if we actually zoomed in, we would get exactly what we got over here on the side. Actually, this is actually already zoomed in. It's just a little more detailed. It's got more of the lines between the numbers, because notice that it goes from -3 to 3, and our graph that we just did went from, actually, yeah, -3 to 3 and -3 to 3. So it's about the same. It's just got a little more detail in there. But notice, like I said before, if I have an initial condition here, it's going to make a curve that looks something, like this, okay? But of course, if I have an initial condition down here, I'm going to have a curve that looks awfully, awfully different, okay? So let's go ahead and let's move on from here. Let's go ahead and erase that. Now, one of the ones that we did before was -x divided by y, and we noticed that that gave us circles, okay? What do you suppose happens if I go x over y? Okay, well, let's go ahead and take a look. Does that surprise us? And the answer is it shouldn't, okay? It shouldn't surprise us that -x over y, if -x over y gives us circles, that x over y gives us, well, let's go ahead and just plot an initial condition. Let's go ahead and plot one here, and then follow the directional cues. Oh, that kind of looks like part of a hyperbola. And remember when we went over conics, we talked about how a hyperbola is an inside-out ellipse. And a circle, of course, is just a particular kind of ellipse. Let's go ahead and actually let's go ahead and do 2x over y. It's not letting me do that, is it? Okay, okay, x over x. Man, this is old school. Okay, but notice how that changed from that, okay? And of course, these are separable differential equations. I could actually go ahead and separate them and solve them and show that to you, which let's go ahead and do at least one of them. Let's go ahead and do the hyperbola that we were just talking about. Oh, I need to unzoom it. Let's get back to a normal zoom. Okay. Now remember that when I had dy dx is equal to -x over y, okay, that became -x dx is equal to y dy. You can integrate both sides. That becomes -x squared dx equals 1/2 y squared. Oh, sorry, that dx needs to go away. Plus c, and multiply through by negative collect terms, and you can go ahead and get x squared plus y squared is equal to some constant, okay? Well, the only thing that happens here, it's exactly the same move if I have x over y, and it winds up being x dx is equal to y dy. Integrate both sides. I'm going to get 1/2 x squared is equal to 1/2 y squared plus c. So I have 1/2 x squared minus 1/2 y squared is equal to c, or x squared minus y squared is equal to c2. Or if I multiply through by a negative, okay, remember that that was that directional field that I showed you was capable not only of doing one of these, right, but notice that it wasn't just horizontal. It actually is a slope field just as much for a vertical. Okay, it just depends on what your constant is. right? Is your constant positive or negative? Which direction is that difference going to be in? Is it going to be x squared y squared in order to give you a positive constant, or is it going to be y squared minus x squared to give you a positive constant? And of course, only solving it will actually tell. That we didn't get as far in this video as I would hope to, but we did actually get through a couple of actually constructing them and talking them through them just a little bit. We'll get on to a little bit of matching in the next video, and from there, for the BC guys, we'll move on to Euler's method, which is yet another approximation method that we're going to have to sort of wrestle with. And it's annoying and burdensome in terms of some of the work if you actually do it by hand, but it really isn't all that bad. But if you have any questions, as always, please do email me. Bye.